In the previous video, we left off at problem 17 and we talked about this idea of matching. Which of these molecules match the NMR the best? And we talked a few things about this point, right? We've talked about identifying the number of signals. We've talked about ranking the signals in terms of frequency. We've looked at the table now, and we've talked about common areas where some of these groups show a signal. And now we've talked about integration. And integration can help us determine which NMR actually goes with which one as well. So with this particular problem, I just want to kind of quickly review the number of signals from each one of these compounds up above. So these are all very symmetrical molecules, each one of these, A, B, C, and D, right? It's almost like I can draw just a line straight in the middle. I can almost call this a meso compound in a way and say that the left-hand side is a perfect match of the right-hand side. So I'm going to get a signal from here because that has a proton. I'm also going to get a signal from here because that's part of the benzene ring. But the next location is the same as the first one. We really do not have OMP here because it is a symmetrical molecule. So if I put a bromine here that is ortho to that C triple bond CH, and then if I put the bromine there, that is still ortho to that carbon triple bond CH. So it would actually be the same equivalent position as far as the benzene ring is going to go. Again, benzene rings causes problems, but in this case, what will help us simplify this down is the term of symmetrical. It's a symmetrical molecule. Symmetries are friend here. So here we get a signal from the CH3 group and the same from a benzene ring, but they're all the same no matter which position that I do. Here we get a signal from the CH2 as well as a signal from the benzene ring. So yet again, two signals. And then finally, I get this CH group that has a signal as well as another signal from the benzene ring. So I'm going to get two signals in total, no matter if it's A, B, C, or D. And if you look at the NMR spectra, there's only two signals that are listed, right? And that is why. So number of signals will not help us to determine which one of these is the best match. So 0 is the TMS, and TMS, remember what that stands for. And then here is one signal, and then here is another signal. Those are the two. All right. So the next thing would be, can we use the location of the chemical shifts to figure out which one that we actually have? Well, let's see. So it looks like we've got here on the left in the more downfield area of the NMR, we have something that's like at a 7.1. So if I look at this chart that I kind of hinted to in the previous video, we need to find something that's like 7.1-ish. And if I look, here's a 6.5 to an 8, right? So that would include a 7.1, and that looks like a hydrogen on a benzene ring. So if I look at this particular NMR again, well, that's not really going to help us, is it? Because this signal, if that is what that is, it is a benzene ring with a hydrogen on it. Well, that one had a hydrogen on the benzene. This one had a hydrogen on the benzene. That one had a hydrogen on the benzene. And this one had a hydrogen on the benzene. So actually, they all would show probably a signal at 7. And that's going to be very difficult for me to see the difference between those four compounds at the top, because they all would bring to the table that 7 point something, okay? So the other signal that we see on the screen looks like a 2.3-ish. So I'm going to go back to this table and I'm going to look for something that's at 2.3. And I'm first going to focus here for A. That A has a carbon triple bond carbon, so an alkyne group. And here is a carbon triple bond carbon, right? And it looks like that has a 2.4 signal. Oh, well, that's really close, right? I mean, if I zoom in here, that's like 2.1, 2.2, 2.3, and that alkyne is going to be a 2.4. So that's maybe a possibility here. Well, let's kind of move on. Let's take a look at the CH3 group. Where do those positions show up? So CH3 group is up here, and that CH3 group shows up at a 0.85. Well, if I look at the NMR, there's no 0.85 in here anywhere. So I can probably just go whoosh, whoosh, get rid of B, because that's not really maybe the proper number, right? And then I continue on to C, and that looks like a chloro group. And I find the chloro group. The chloro group is here. And that chloro group says it should have a signal between 3 to 4. All right. So that proton on a carbon with a chloro group, that's what we have here. That's going to be higher than what's stated here on the screen. So I probably could do that number too as well with it. And then we take a look at D, and that looks like bromine. So bromine is a 2.5 to a 4. And here we see a 2.5. So 2.1, 2.2, 2.3, 2.4, 2.5 is right there. So 2.5 to a 4 is going to be bromine. And that really falls before the typical bromine type of signal does. So at first glance, I could probably say, get rid of that. And it looks like, based on the signal, that the proper choice here is going to be A, and that is a ring with an alkyne group. So that ring is the benzene ring. That benzene ring should have a hydrogen on a benzene of 6.5 to 8, and we do have it, 7.1-ish. And then we have an alkyne, and that alkyne group is going to be here, a hydrogen on an alkyne, and that's at a 2.4. So here's our hydrogen on the alkyne, and that should be about a 2.4-ish. Now, to go another step further, I could also use integration in order to help determine if this actually is in fact the proper molecule or not. I'm just basing this off of hunches. That's all I'm doing. Just some table data and traditional signals where these appear. So integration would also help us, but folks, in order to do integration, I would need really numbers here that's associated with each one of these signals, and I don't have that. I need to be provided that, and it doesn't really tell me what that is. So without those values, I cannot calculate a ratio, and if I can't calculate a ratio, I would not be able to calculate and match A, B, C, or D with it. So in other words, up here at the top, if I wanted to integrate this, well, this would be a hydrogen and that would be a hydrogen. They're equivalent. So that would be a 2. And then here on the benzene ring, 1, 2, 3, and a 4. So that's a 2 to 4, which breaks down to a 1 to 2 ratio. All right. If I do this mix for B, that's 3 to the left and 3 to the right. So that's 6. And most of the time we put the smaller numbers first. So the benzene ring is going to be 4. So 4 to 6, well, 2 goes into 4 2 times, and 2 goes into 6 3 times. So that would be a 2 to 3 ratio. And then if I take a look at C, I've got 2 to the left and 2 to the right, so that's 4. And then on the benzene ring, I have 4 more, right? 1, 2, 3, and 4. So divide by the smaller number, that is a 1 to 1 ratio. And then if I look at the D part, I'll see 1 to the left and 1 to the right. So that's a total of 2. And then on the benzene ring, I see 1, 2, 3, and 4. So that is also a 4 position. And that 2 to 4 will break down to a 1 and 2 position. So I could use maybe the integration to help determine if I've got the right answer or not. But keep in mind that the bromo group has the same integration ratio as the alkyne group. They're both 1 to 2s. The difference is that the alkyne would have a different signal than the bromine. All right. So this is the order of thinking that we need to go through in terms of NMR. Look at the number of signals. Once I find that, I then look at where those signals are located, see what possibly could be there, and then maybe, just maybe, use integration to help confirm that answer that I'm getting ready to make. And in this case, I could not do that because they couldn't give me the values on the screen. All right. So the next video that we're going to focus on is something called splitting. Okay, the world of NMR is full of splits. I can't do a split, can you? Maybe if I tried. Maybe if I tried really good, I could do a split. I used to be able to do a split, but maybe not so more in my old crabby age. So if we take a look at the split is going to give rise to more information out of the NMR. And I need to take a look at splitting. I need to understand what splitting means, and I will be able to take away more information from the spectrum of the NMR versus if I didn't know what splitting was. And it will help us kind of confirm the structure that has been analyzed in order to obtain that NMR. And we'll be able to predict splitting as well by looking at a molecule. So I'm not going to go into that with this video. This video is going to cut kind of short. And in the next video, we'll start this topic of splitting. What is it? What does it do? How can we pick it up? And how can we calculate it? Because yet again, it's something that we do have to calculate. And it's a doozy, folks. So be ready. Rest up. Crack those knuckles. I'll be back when you're ready.